So welcome back. After 40 minutes it get disconnected, so I connected back again. So we were dealing with respect to our multi-lever platform scale, right? So is it recorded? Okay. So now it is T into C. For the second platform where you are assigning the unknown weight W1 and W2. So the entire tension into the constraint distance what we are using. So this is the tension associated into the C because we are fixing the constraint over here to calculate the bending moment at the equilibrium. So T into C will be equal to W1 into F. Again we have to check this distance. So this is D by E. So you will get T into C equal to W1 into F into D upon E. So this distance also should be considered because we are referring to this constraint and not to this. So it will be W1 into F D into E. And next we have to go for the W2. So W2 is near to the constraint what we were referring. So this will be equal to W2 into H. So previously we referred this constraint, okay, and now we are referring to this constraint. So for the moment equation it will be T into this entire constraint distance C. Okay, that will be equal to W1 into F into times of D into E plus W2 into H. So this will be the equation second and 1. So if the links are so proportion, then what we do? Okay, so we will take this equation, compare both of the things, then you will get T into C, okay, will be equal to, so you have W1 and W2. So H is common in both the cases. Okay, so here you have to, no, just a second. If the links are so proportion that H by E, okay, you have to take H by E is equal to F upon D, right? So you have H and you have E here. So H upon E will be equal to F upon D. So this is the proportion what they are assuming for both the platforms. So this is one arm balancing and this is a second platform in which we are adding the weights. So to be both in proportion, so this is the constraint what we have to follow. So H upon E should be equal to F upon D. So based on this equation, then the equation gets changed to T into C is equal to H into W1 plus W2 times H of W. So from the equation 3, what we will understand is the weight W may be placed anywhere on the platform and its position relative to the knife edges of the platform is immaterial. So what does it tells? On the platform here, so weight W could be placed at any position. You are not having any relation which will affect the balancing of the arm here across the poise weight and the pan weight. So by this equation it will be clear that the weight can be placed anywhere in the platform and its position relative to the knife edges of the platform is immaterial, means it is not affecting any way. Okay, so T can be eliminated from the equations. That means to say the tensional force which was originated due to the balanced arm with the effect of the pan weights is not related to the platform what we are associating here for the bifurcation of the weight into W1 and W2. It is not related nowhere. So you can place W in any position. Only thing we have to see that balancing the poise weight with the addition of the pan weight initially. So that is enough. Even though it is connected to the constraint over here on which it has been pivoted to platforms, this tensional force generated in the arm is not making much effect on the platforms which are embedded. above the constraint, and hence you can place W at any position and it is not related to the tension created across the balancing arm. So that's what been explained, and hence the value of T can be eliminated from both the equations 1 and 3. And hence when you eliminate the value of T, so equation get reduced into this way. So in that we can determine what is the value of the unknown weight. So the unknown weight will be determined from this equation. So this equation is also called as a multiplication rotation of the scale. So multiplication rotation is represented from here onwards as M. So what it that indicate? So this is indicative of the weight that should be put in the pan to balance the weight on the platform. So this value of M, what we calculate theoretically, will help us in adding the weight into the pan weight. So this tensional force will not affect nowhere. You can place the value of W anywhere and you just balance it with the balancing arm just by adding extra weights to the pan such that the poise weight always remains 0. So this is the constraint what we have to follow, and T value will not come into picture. So that is what being explained. Suppose the scale has a multiplication ratio of 1000. It means that weight of 1 kg put in the pan can be balanced a weight of 1000 kg put on the platform. So what do you mean? If the multiplication ratio is defined as 1000, it means that weight of 1 kg what you add in the pan can balance the weight of 1000 kg what you are putting on the platform. So it is a multiplication ratio what you have to understand. So if you put 1 kg here, it can balance of around 1000 kg of weight what you put on the platform. So you can bifurcate that equally into W1 and W2, 500 and 500 here. By adding 1 kg at the pan weight, you can balance it such that the poise weight will be 0 here. So this is what being told. So it means that 1 kg put in the pan can balance 1000 kg put on the platform. So scales are available which have multiplication ratios as high as 10,000. So we just spoke for 1000. Similarly, you have the multiplication ratio scales until 10,000. So you can guess how much huge amount of weight you can measure by using multi-lever platform scale method. So this multiplication ratio M always is an indicative of weight that should be put in the pan to balance the weight of the platform. So same thing is being told. Here you have to worry about this equation. Okay. So scales are available which have multiplication ratios as high as 10,000. This also we told. If the beam scale is so divided that a moment of poise weight WP by 1 scale division represents a force for 1 kg. So if the poise value is 0, everything is balanced, and if it shows on the scale as 1, then what does it indicates? It represents a force for 1 kg. The scale what we read out in multi-lever platform scale, for every scale of unit it represents 1 kg. Then a poise moment of Y scale division should produce the same result as the poise weight applied in the pan. So both the things should show the same result. So if it is showing 1 kg, so when you add some other weight on the poise, so it has to show that variation in the poise weight as well. So this variation in the scale keep on moving as you vary the addition of the load in the platform. So you can weigh, if you add 10,000 weight here, so accordingly you should add 1000 kg on the pan weight. So it shows what is the variation, the measurement of force on the scale. So if it moves 1 unit, then it is of 1 kg. So if it you moves more than 1 unit, accordingly you have to consider what is being the applied force in terms of kgs. Hence, the above equation is represented by a relationship that determines the required scale divisions on the beam for any poise weight. So, we follow a equation here. So, poise weight into the distance y will be always equal to x, y and a, or else you will determine x is equal to poise weight divided by a. So, y here gets cancelled. Okay, so this is how you have to consider in determining what is the how the variation in the poise weight do come. So first we explained how to operate the multi-lever platform scale, for which it is being used, how you balance to get the equilibrium in the balance arm, how you will place the weight on the platform. After applying the weight on the platform, how do you calibrate again to make WP to reach zero value. Then you will apply the moment equation, then you will equate with the proportionality constraint given. Then we will come to know that the value of T is not making any effect on the platform in which you are embedding the weights, and hence we will neglect the tensional force from the equations, and then you will get only the relation in which you can determine the unknown weight. So with the help of unknown weight, we will tell what do you mean by M, which is nothing but the multiplication ratio. So how you have to play with multiplication ratio to add the weights on the pan such that unknown mass what you apply in the platform could be balanced and its value could be determined, and how the variation in the poise scale goes on with the addition of the weights. So every scale tell you the reading with respect to the force applied on the arm in terms of kg. So this movement along the y-axis, okay, similar movement along the x-axis will also be shown. So here you have an poise scale. So this movement will show the variation in the x-axis. Okay, so that value of x you will take it out, how many divisions it has been moving. So similarly after that you will this value of y what you consider will be same in both the directions, it gets cancelled, only you will be affected with determining the value of x. So this x value will be determined upon poise weight divided by A. Okay, so what is A over here? So you have the constraint which has been located from the knife edge to that of the pan weights. So this will be the value of A. So finally, this is how you will segregate the given weight into W1 and W2 and identify its value, how it is varying, what is the effect of the load, what is the measurement of the force with the help of the poise scale, which each scale shows you the equivalent force measured in terms of kgs. So this is about multi-lever platform scale. Apart from that, you have one more thing, what we call it as spring gauge. So if we go here to our classifications back, so we covered related to scales and balances where we had three types. One is equal arm, unequal arm and multi-lever platform scale, right? So after that the other type of force measurement is through elastic force meter. In that we have one classification what we call it as a spring scale. So one example for the spring scale is nothing but our spring gauge. So everyone knows, many of you might have operated also how does a spring gauge works. So just to show Exactly, how does it work? So it is called as an elastic force meter, where we will be using a spring gauge. So you'll be having a spring and the stiffness of the spring will be known. So when you add on some load to it, the spring gets expanded down. So then you will measure the value of what is the load being applied on it. So this is a normal spring gauge, even you might have used many times in your day-to-day activities or in the laboratories. So this is one of the method what I just wanted to tell you. Anyhow, the description related to this is not there in the syllabus, but as per the classification, this is also one of the category which uses the elastic force meter. So that I just wanted to tell you about. So then the other classification is our load cells. So what do you mean by a load cell? Right, so under load cell we have four categories. So these are strain gauge, hydraulic, pneumatic and LVDT. So all these comes under the category of load cell, which helps in checking the load added to it and do the calibration part also. So what do you mean by a load cell? So load cell is also a particular type of transducer. We have studied what you mean by a transducer, which will sense and convert that into the required output signal. So it is specifically called to be as a force transducer. All the load cells which come across comes into the family of transducer, into that specifically for force transducer, because it converts a force. It could be either tensional force, compression, pressure or the torque into the electrical signal, so which could be measured and standardized, and hence this is the application of the load cell. So it uses the force in any means and convert that into the electrical signal, which could be easily measured. So this is the main application of the load cell. So under load cell I told you different categories. In that, one is the strain gauge load cell. For that you should know what you mean by a strain gauge. As the name itself suggests, this is a device which has been used to measure the strain of a particular object. So it was invented in the year 1938 by Edward and Arthur. Okay, so yeah, for the strain gauge measurement, again there is a need of using Wheatstone bridge. Everyone is aware of what you mean by a Wheatstone bridge. You have studied in your 11th, 12th and also in your first year subjects. So what happens? As the object is deformed, the spring also gets deformed. What does it results? It results in causing electrical resistance to change. So the resistance change usually is measured by using our Wheatstone bridge. So it is related to the strain by the quantity known as the gauge factor. So whenever you pass a current through the Wheatstone bridge, it shows some resistance for the flow of, and that is also measured with the help of the gauge factor. So how does a strain gauge deformation takes place? So before that, you can see this is a Wheatstone bridge which will be having four legs, R1, R2, R3 and R4. It has to be balanced. So what is the main use of Wheatstone bridge? It is an electrical circuit which is used to measure an unknown electrical resistance. By you have to balance at least minimum two legs of the given bridge. So one leg of which will include the unknown component what you have to measure. So this is about the Wheatstone bridge. So the strain gauge deformation could be either the tension or could be the compression force. So I told you already, it can sense the tensional force, compression, pressure or torque, which will be later converted into the electrical signal. So this is how the strain gauge deformation takes place. Okay, so now before going into the strain gauge load cell, just focus on the Wheatstone bridge. So the excitation voltage is represented by V suffix EX. It is also known constant. So okay, and the output voltage will be represented by V naught. So E is variable depending upon the shape of the strain gauges. So depending upon the shape of the strain gauges you use, the output voltage will be varied. Okay. So if all the resistors are balanced in the Wheatstone network, then it is assumed that R1 by R2 is equal to R3 by R4. In that case, what happens? Our output voltage remains zero. Then we can say that the given Wheatstone bridge is balanced. Suppose if the resistance is even one of the resistor changes, so then output also will change. It won't be equal to zero. So if initially you balance it with this equilibrium condition, and if you suppose change one of the resistors value, so then the V naught will not remains the same. It will change it accordingly. So the change in the output voltage can be measured and interrupted by using the Ohm's law. So Ohm's law, everyone know V is equal to Ri. So what does the Ohm's law states? The Ohm's law states that the current running through the conductor between the 2 points is directly proportional to the voltage induced across the 2 points. Resistance is introduced as a constant in the relationship, which is independent of the current, and hence the Ohm's law is expressed in the equation I is equal to V upon R. So same concept if you apply for the 4 resistance in the Wheatstone bridge circuit, then the output voltage what we determine using the Wheatstone bridge will be equal to R3 upon R3 plus R4 minus R2 upon R1 plus R2 into the excitation voltage V suffix EX. Okay, this is how we determine the output voltage when there is a variation in the balanced circuit, balanced bridge. Suppose one of the resistance has to be is unknown and you have to determine. So then you have to change accordingly. When the changed value will be substituted here in the equation to evaluate what is the output voltage. So this is the means of how to evaluate the output voltage when the Wheatstone bridge is balanced or unbalanced. So this is about the Wheatstone bridge and the strain gauge. So now we have to relate that into our load cell. So in a load cell, the resistors here will be replaced by the strain gauges and arranged in alternating tension and compression formation, because I told you the strain gauges will show the tension deformation as well as the compression deformation, where there will be an longer and thinner wire here and it will be shorter and thicker wire here due to the compressed force and due to the tensional force. So here the resistors which were there in the Wheatstone bridge will be replaced by the strain gauges in case of strain gauge load cell. So which will be alternatively arranged. So one you have tension, the other one will be compression, and again tension and again compression. In case of the strain gauges, what you replace from R1, R2, R3 and R4. So when force is exerted on this kind of load cell, the structure and the resistance of the strain gauge changes, and once it has been changed, we will evaluate the output voltage. Okay, so from the resulting data, output voltage can be determined by using the equation which has been shown. So you will be just replacing these resistors by the strain gauges and you will determine the output voltage with respect to the deformation which happens in our strain gauge. So it could be due to the tensional force and also the compressional force. So this is how the Wheatstone bridge looks for strain gauge load cell. So where you will be having R1 associated with compression, R4 with tension, here again R2 with tension and R3 with compression. So you will align deadly opposite to each other. So this will be the excitation voltage which helps in deforming the strain gauge load cell, and here is the output voltage what you determine based on the equation which was explained to you all. So now let us just focus some aspects related to strain gauge. So when force is exerted on the strain gauge load cell, the spring elements is slightly deformed. So you will be having the spring elements in the strain gauge, right? So this will be slightly deformed, and unless overloaded, always it returns to original shape. If it is loaded to a very reasonable value, so then it deforms and it comes back to its original shape. If it is overloaded, it always returns to its, if it is not overloaded, it will return to its original shape. So as the spring elements deform, what happens? The strain gauges also changes the shape. So the resulting alteration to the resistance in the strain gauges can be measured by the output voltage. As I told you, so the variation in the spring could be measured here in our output voltage. So the change in voltage is always proportional to the amount of force,
It's 10:40, ma'am.
yeah, just a second, amount of force applied to the cell. Thus the amount of force can be calculated from the load cell output. So the voltage which has been proportional to the force applied can be calculated from the load cell output. So this is how a strain gauge load cell looks like. And here another diagram which relates the actual load cell package, how does it look like, and the inbuilt Wheatstone bridge circuit. So for balancing of the Wheatstone bridge circuit, we referred this output equation already. So if they ask you to explain the strain gauge load cell, just speak about the strain gauge, throw some concept on Wheatstone bridge, and show how the Wheatstone bridge is replaced with strain gauge load cell and how you determine the output voltage. So this is about the strain gauge load cell, and so in the next classes we deal about the other types of load cells and then go for the measurement of torque and pressure. So I'll end here, and one more thing what I wanted to tell is, as per the meeting, so we have to conduct one quiz after every fourth hour of the class in a week. But in our credit we have 3 classes. So at the end of the third hour of the class, we have to conduct a small quiz. So what I'll be doing is, now the time is over, I will just share you a Google form with around 8 to 10 questions associated with the last module or fifth module. I will just tell which module it is. You kindly answer the quizzes so that that could also be considered as a part of your IA marks, because now we are not considering the PBL marks related to this semesters, and as it is told, along with the online internals, the quiz every week we have to take it, and that has to be considered as a part of our IA marks. So I will share you the link in the Google Classroom through which you have to attend the quiz. And tomorrow I will be handling the practical session for y'all. I will just tell you the time and the link and which experiment I'll be doing. I'll also share you the this one lab manual for y'all. So we'll just try to complete one experiment tomorrow. So I will tell you, it will be in the afternoon session, hopefully from 2 o'clock. I will send you the link either through the Google Meet or through the Zoom class, whichever is convenient. So I will inform you by the end of the day or tomorrow morning, but we'll be having one practical session tomorrow in the afternoon. So I hope I've taken much of your time because there was some interruption in between. I'm sorry. So everyone, please take care and be safe. So let us see tomorrow in the practical session. Thank you. Bye bye.
When is the quiz, ma'am?
Which quiz?
You just told us a quiz, right?
Yeah. The quiz, we are supposed to do it on the last hour of the week session. So this week we have covered already, right? The 3 hours. So I was supposed to take today only. So within the class hours also we can take it. But if we take like that, we can't complete the subject syllabus also. So I will share in the Google link. So you that will be like a course exit survey link what you have used already, right? So we will just click the objective answers. It will be just theoretical concepts. Just go through it and submit. I will put that also in the WhatsApp group. Hopefully by today. If it is not possible, you can do it by tomorrow also. Okay.
Ma'am, can that happen after internals, ma'am?
After internals you have time still, right? It is 29th today. You have 1 second. Okay, I'll
But
just
still,
speak.
ma'am.
Yeah, yeah. Let me see, or else I will just speak with the HOD. If he tells okay, we can do it after the internals, we'll keep it after the internals. Within this week means then
Okay.
you need to do it. I'll just update you whatever it is. Okay.
Okay, ma'am.
Yeah, fine then. Take care, everyone. Be safe. Study well. Thank you. Bye bye.
Thank you, ma'am.
Yeah, bye.
Thank you, ma'am.
Yeah, bye.